Well, the eagle-eyed among our viewers will have spotted that today's radio is made by the General Electric Company Limited, a stalwart of British industry, born on the eve of the 20th century, strangled by financial speculation on the eve of the 21st century. A sad tale overall, but in between they made some quite good consumer electronics, and this is an example of it, I think, from the late 1960s. It's a three-way band radio. I think it's got a nice clear scale. It's got a provision for plugging external AM and FM aerials, which is quite a rarity at that time, really. It's got the usual GEC had this odd thing. Most people have the on and off switch on the volume control. They had it on the tone control. And then you've got the bands on the top here. And, oh, that's an interesting little historical thing. I mentioned a couple of times in these things about the wavelength changeovers that took place in the 1970s, and the BBC sent out lots of little stickers, and this obviously has still got the one on it telling you where all the frequencies have moved to. Now you'll also notice, as well as the long wave and medium wave and FM here, you've got a fourth button called BS. Now this isn't a thing that takes you to an erudite discussion of postmodern architecture on Radio 4. What it actually stands for is band spread, and the reason it's there is if you look at the medium wave bit, there were a lot of stations crowded around this bit here and below that, so this only goes down to 200 meters on medium wave, and what happens is when you press the BS you get access to all that bit, so it's basically going from here 175 up to Luxembourg, which would have been 208, is all split out, so you get the entire scale you can use for tuning, and it makes it easy to separate all the stations that were down here, of which there were quite a few, including pirate stations at that time. Now trying it out, we do get sound, but it's a bit intermittent on long wave and medium wave. We get nothing on FM. Now the intermittent sound, which seems to go away or come back if you hit it, gives me a clue as to what the problem is. One of the things about these radios is that they contain quite a lot of germanium. Not geraniums, no, germanium. That was the material we used to make transistors before silicon was practical to use for that purpose. I often wonder whether Germanium Valley would have been a really pleasant place and not the moral cesspit that Silicon Valley has become, but we're not here to discuss such thoughts. Now there were two big problems with the germanium transistors. One of them was that they were quite heat sensitive, so when you're soldering them you have to be quite careful not to destroy them with the heat from the soldering iron. So in fact what you used to have, and I've still got one of these, is this thing called a heat shunt, and you used to clip that around the lead of the transistor while you were soldering it, so that all the heat from the soldering iron was diverted into there and didn't damage the transistor. The other thing is that if you look at a modern set of silicon transistors, here's some silicon transistors, and they're all encased in plastic, right? These are modern transistors. A lot of the early germanium ones were actually encased in a metal can, and what used to happen was for some reason they grow like tin whiskers inside there, which would short out the transistor to the can. And this was a big problem. NASA did a lot of investigation into it, never really came to conclusions why it happened, because it did actually affect the space program at some point. Anyway, I think that's likely to be the problem with this. I'm going to take the back off and see if that really is the case. Now the back of the case was designed to come off quite easily with two coin operatable screws. Actually only one in this case because one of them has gone missing. And here we are. This is the innards of the thing. It has this lovely 1960s radio smell that I simply cannot convey in this medium, but believe me, it's good. But one of the things we're going to do is, if I turn this back on, you can see that we're not getting any sound at the moment. So it's not a bit too loud there. Now what I'm going to do, see this transistor here. See, I tap that and all the radio's gone away again. And I tap it again, it comes back. Now that is an absolute total indicator of the tin whisker effect. What's happening is I tap that, the tin whiskers move around a bit and unshort, and then I tap it again and they short out again. So this little germanium transistor here, I don't know if you can quite see that, this one, then AF117, this would have been quite a common thing in these radios at the time. Why don't we just go another one? Well, nobody makes them anymore. Once people started moving over to using silicon transistors, germanium transistors sort of went out of use. You can get hold of them because people take them out of old radios like this that have been scrapped and other equipment and sell them on eBay. But basically, what's the point of replacing a worn out 50-year-old transistor with another worn out 50-year-old transistor? There's a lot of silicon and germanium transistors have different characteristics. So what a lot of people will tell you is you can't interchange them. You have to redesign the circuit and get the bias levels right. Well, that's sometimes the case, not always in my view. But in any case, I'm going to swap this out for a silicon transistor because it's not working at the moment. And the worst that can happen is it doesn't work afterwards. But it might work, or we might have to do some adjustments. So let's do that. Okay, well, I've changed the transistor. You can just about see it here. That's a little black silicon transistor in place of that great big old metal germanium thing. Now, courtesy of this excellent website which allows you to download manuals for lots of the old radios, I have the service manual for this. 3 shillings and sixpence it cost back in the day. That's 17.5 new pence in today's money. That, I think, would have been in 1966, because I just see this reference right at the end of it here. And the service manual website is still very good value. It did cost more than 17.5 pence, but £2 isn't bad. And they've got loads of stuff on there. But what this does do is it allows me to, well, it's got a very nice description of how the circuits work in it, and all the adjustment process, but also we get the circuit diagrams, and around the circuit diagrams, around the transistor we've replaced, which is this one, it gives us a few voltages. Now, what I couldn't work out is why there'd be 9 volts here when I would have thought that was connected to ground, but what they've done is measured the voltages upside down. So the note says that the voltages are all measured relative to the plus 9 volt supply line. So that's why that's showing as plus 9 volts. So you have to measure everything from the top of the battery, not the bottom. So the next thing to do is measure the voltages around this transistor that we've just replaced and see what the changes are and whether they're what we'd expect. Right, so we're going to measure off here's a positive rail, like it tells us to measure from. Here is the collector of TR3, and we get 8.82 volts. The battery is running down a bit here actually, so that's why I think actually we've not got quite a full battery. So that's fine. And then on the base it says there should be 3.35. So let's go to the base, and we get 3.7, 3.72. But that's not a surprise, and I'll go through that in a moment. And then on the emitter, let's just have a look on the emitter, we're getting 3.19, and the diagram says it should be 3.25, given that we're a little bit low on the voltage anyway. That's pretty much what I'd expect. Now, what you do notice, of course, is a slight difference here. So going across the base, so the emitter's 3.19. The base is 3.72, right? So 3.1, 3.7, well, 3.2, 3.7, 0.5, 0.6, you're seeing difference. If you looked at the original one, it was saying 3.35 and 3.25. Now, the reason for this is that this is the difference between a germanium and a silicon transistor. Silicon transistors have a bigger voltage drop across the base emitter junction than do germanium transistors. So this is a difference that you'll get. So I'm not bothered about that. That voltage change is pretty much what I expect. Of course, that's all like static voltages. What we need to do now is find out what happens when we actually listen to it. Do we get any signal? So let's turn the volume up. Now it's a bit rubbishy. I can't really tell whether it's working or not. Partly because I haven't got the pointer. Oh, I've got the pointer, but I haven't got the scale to tell me what frequency I'm on. What I'm going to do, therefore, is this thing has an intermediate frequency that everything is shifted down to a 470 kilohertz. So if I look on the collector of that, if I go back to the collector here and I put it on the scope, and there's definitely an oscillation there. What I'll do is I'll just stick this on auto range. So this is the oscillator stage, and it oscillates at 470 kilohertz above the frequency that you're tuned to. And if you look at the frequency measurement here at the bottom, right here, you can see it's on 1.371 megahertz. Now 5 Live is on 909, so what I need to get is 909 plus 470, which is 1379. So if I tune this so that it's on 1379, I should be pretty close to 5 Live. So that's probably as close as I can get it, really. So then I'm going to see if there's actually any program. And you can hear it there. So looks to me like it is working. I think once we put it back together, it should be fine. Once we get it into a decent reception area free from interference.